Okay. All right. Sorry. Just because I think so. Let me see the people. Yeah. So just a reminder that on Friday there's going to be a discussion on black hole information loss, and the link will be sent to you via email. And so yeah. So for those of you who are interested, you can you're very welcome to join. Okay, great. So starting from today, we're going to move beyond black hole solutions and come back to gravity around flat space. And so we're going to talk about gravity around flat background. So I'll be explicit in a moment. So what do I mean? Well, we're going to talk about. So of course, everything I did here, you can do it on a curved background. So in other words, you can do the same thing for example, around black hole backgrounds, and this will be something that that corresponds to perturbations around black hole. So just to set up the discussion, we'll first start with perturbations around the flat background. So we start with, of course, we start with the Einstein-Hilbert action. And so the idea is, and this is similar to what I've discussed in the quantum field theory class, which is that whenever you, so of course, this is our Einstein-Hilbert action, this is our Lagrangian. Usually when we write down our Lagrangian, we write down our, let me just first write down as a function of our field. And when we write this down, what we really mean is that the field is given by, let me write this as a background value plus fluctuations. And if you think about it as an action, fluctuation. So, or let me write this as, okay. And so when you do, as most of you know, when you write down an action and you write down a Lagrangian, you put it in a path integral, you integrate it. What you're integrating in most cases, integrating over this fluctuation. Okay. Of course, in generic, in the most simplest case, our background is usually 0. We usually set our background to be 0. So then there's no difference between the fluctuation and the field itself. Okay, this is the usual situation when we deal with in field theory, but gravity is slightly different, because if we're doing the same thing with gravity, so now instead of just some scalar field, we have a field that is our metric. Then we want to separate our metric into something that is the background. Let me just call it background, and then something called the fluctuation. Right now, so what is the background? The background has to be a solution to the equation of motion, And a solution to the equation, well, what is the equation of motion? Well, the equation of motion is basically Einstein equation, right? Okay, so the most simplest solution to Einstein equation is not that the background, the background is a metric, so you cannot put the metric to 0, right? Then what are we talking about? Well, there's no sense in which the metric is 0. So the simplest background is of course, that the metric is asymptotic. If you want to have some kind of asymptotic flat region, then the simplest background is just the flat space metric. Okay. So we usually write, oh, sorry, what am I doing? The indices are downstairs. So what we do is that we take the background to be the flat part, and then we do the fluctuation. We write down the fluctuation here. Now I'm going to normalize this by kappa for a reason that you'll see shortly. Okay. But this will be the way that you talk about perturbations in gravity, is that you have some background value and then you talk about the fluctuation. And therefore, that means that your Lagrangian, you're going to you're going to write it, you're going to write it as eta plus kappa h. And then you're going to expand, and then you're going to expand in h. Okay, so basically what we're going to have is we're going to have g mu nu is equal to the flat space part plus the fluctuation part. Of course, when you have the metric, you also need the inverse metric, right? So you also have the g mu nu. Now the point here is that you want it to be since you already identify your field, the degree of freedom, that I mean the fluctuation degree of freedom here. So that means that the g mu nu upstairs, which is the inverse of the g mu nu downstairs, you want to write it in terms of this h mu nu as well. Okay, so that means that you want to write it as h mu nu. Eta mu nu. The first term is of course minus kappa h mu nu. Remember that what are we doing? We're trying to ensure that this is delta rho mu, right? So the first linear term is, what am I writing? So the first linear term is this upstairs, where h mu nu is just eta mu rho eta nu sigma on h rho sigma. Okay, so even though I write it upstairs, it's really just linearly proportional to the thing downstairs. Okay. So of course, then if I contract this guy, so if I contract this guy with this guy, I plug it in here, I'm going to solve this equation at least up to linear order, right? But of course, there's higher order terms because of course you're going to have h mu nu multiplied by h nu nu. So basically what you have is you're going to have if you start with the linear perturbation here, then your inverse metric is going to have your upper metric is going to have terms that are of order higher. There's going to be an infinite order of h. There's going to be an infinite order in expansion in h for the inverse metric. Okay, and this is usually what is the most complicated part about GR when we're doing perturbation, is that in principle you have an infinite number of in terms of the perturbed field, the inverse metric is going to have an infinite order of expansion. So in other words, it's going to look like something that looks like this. This is just schematic. You're going to have something that like this, kappa cube h cube, and then an infinite order all the way out. Okay. So of course, once you have this and you have this, then all you need to do is just take this, take these new representation, and you just plug it back into your Einstein-Hilbert action, and then you expand out. So in terms of this perturbation, in terms of this perturbation field, that usually what the Einstein-Hilbert action will look like. Now you understand why I have this kappa here. So let's write it out. So we know that so this will be done. Let me just write this out schematically. So I'm not going to be very careful about indices because there's a lot of them. So roughly speaking, what you're going to get is so remember that this was kappa square, 2 kappa square. Now remember what was, we have the square root of determinant of G. Remember, so this is G mu nu here. There should be a minus. Your R, what is R? R is, so R is basically a function of G, but since R is basically G inverse, so let me just write G inverse 2 derivatives on G. So roughly speaking, it looks like this. Of course, there's a lot of different index contraction. Therefore, when you plug this into, expansion, plug these two things in your R, that means that first of all, at linear order, now you see why I have the, sorry, what am I writing here? Why do I have? Okay. So at linear order, you're going to get, now you see why I'm putting K here. Because if I have a kappa H and then I have a kappa H here, so each H comes with this kappa. So that means that at linear order, you're going to get dx, d. So at linear, sorry, at the quadratic order, you're going to get something like this. Right? So the kappa square cancels. So you get the usual kinetic term for any field theory. So this is almost, for those of you who've seen Klein-Gordon equation before, you know that you basically have two fields with two derivatives between them. Okay, so this kappa square cancels out. That gives you the canonical. So these kappa, if you normalize your field by kappa, and actually this is also needed for dimension analysis to ensure that your field has the correct dimension. Okay, so this is going to be your kinetic term. And then, of course, as you got, because of the very simple fact that you have an infinite expansion here, you have an infinite expansion here. That means that what you're going to do, you're going to have H partial H, for example, with various contraction kappa plus kappa square. Let me just H. I'm going to write this arbitrarily. And you're going to have infinite expansion, right? So you're going to have kappa cube, H partial H, H. So basically what you're going to have is you're going to get kappa to the n. So if you have n of them, and then you're going to have H to the n plus 2, and then you're going to have two derivatives. So each term is going to look something like this in your expansion. So this is one of the difficult things about even just talking about gravity and around flat space, is that the Lagrangian you're working with has an infinite number of interaction terms. So this never ends. Okay, and this is of course intimately tied to the usual statement that you hear about that gravity is non-renormalizable, that gravity has problem when the energy is large. And so you can already see this problem just from this fact that you have this infinite expansion. Okay, so is this structure clear? So this, when people talk about trying to solve quantum gravity, in some cases, people try to understand this structure, this infinite expansion structure. Is there any questions? Is this structure clear for you guys? Is it straightforward, or you're confused about what I'm doing?
I wonder that the partial sign of the order of the partial sign doesn't matter.
Yeah, of course it matters. I'm just doing schematically. So I'm just
Okay.
counting the number of the derivatives. So this is schematically.
Okay.
Okay, yes, it's so for each of these terms, there's a lot of them. Then you need to find all the different contraction. So for example, if you write down this term and you write down all the possible all the contractions that are involved here, it's going to take a page. Okay, so there's already, of course, it depends on which kind of gauge you choose, but this is already a page here. And of course, you don't know how many pages you have here. And then, of course, then this just goes on and on forever. Okay. Is there any other questions? Well, I mean, if you guys like, well, let me just send you guys, I'll find a reference. I'll send you guys the page of formulas for just this interaction alone, so you can understand how complicated this is. But do you guys see why it's so complicated? Anyone? Why do we have this infinite number of fields here? I just mentioned it actually in the beginning.
Because it's just an effective theory.
Sorry?
Because the Einstein-Hilbert reaction is just an effective theory.
Well, no, I mean, that's related to the fact that you expect that you're going to have non-renormalizable theory, and so therefore you're going to expect you have this plus r squared plus r cubed with various derivative on r4. And you can have write down infinite number of terms that adds to the Einstein-Hilbert action. But I'm asking that just the Einstein-Hilbert action alone, when you do perturbation, you have infinite number of terms. So it's not about these guys. So it's just even Einstein-Hilbert theory alone has these infinite number of terms.
The inverse metric.
Yeah, exactly. It's the inverse metric. Okay, it's just that because that you have both G mu nu and G nu nu. So even if you choose to just write the perturbation as a linear expansion, as we usually do in quantum field theory, because of the very fact that you have the inverse metric, will tell you that you're going to have infinite number of terms. Okay, said in another way, you have this metric and you write down its inverse. The inverse involves the inverse of determinant, right? I mean, that's, if you write down the inverse of a metric, it's proportional to the inverse of the determinant of the original metric, right? And then you expand out that determinant, you're going to get an infinite number of terms. Okay, I mean, GR is very complicated in various directions, but in various directions, it's important to understand why it's complicated. So you know what's the physics behind that complication. Okay, so this infinite expansion has nothing to do with whether or not the theory is, I mean, it's nothing to do with the fact that you can add an infinite number of higher dimension operators. These are completely two separate things. Okay. Any questions? Okay, then let's just stick to linear part first. So this is called linearized gravity, which means you notice that most of these, all of these things are higher and higher order in kappa. Okay, so for now I'm going to just think about the leading term. So even just the dynamical term, which is just this term, is sufficiently complicated. So we're going to talk about the linearized gravity, which is a simplification of this entire infinite expansion. So we can do this in terms of linearized gravity. So first of all, let's start. Okay, so that means that in both cases, we're only considering up to linear order term. So that means that I'm erasing this guy. So I'm just going to truncate everything. I'm just going to truncate at linear order. So now things are easier. Okay, so I'm only going to truncate to, only going to keep these two terms, and this to do for the inverse metric. So for linearized gravity, that means, for example, our Christoffel symbol. So let's start with the Christoffel symbol. So the Christoffel symbol, well, I mean, you guys know the original formula, right? So the original formula is just G rho lambda partial mu G nu lambda, where this is symmetrized, and then minus partial lambda G mu nu. Okay, now let's linearize it. Linear. So if you linearize this, first of all, since this is a derivative, so the derivative has to hit something, right? Since this is a derivative, it has to hit something. So that means this, you need h here. Now, since we're only talking about things up to linear order in h, that means that for this guy, the inverse metric, you only keep the eta rho lambda. Is that clear? Okay, because we're just keeping things up to linear order. So up to linear orders, I mean, you cannot have eta here because it's the derivative acting on eta is 0. Okay, so you cannot have eta here. So that means the for the linearized metric, this is a linearized Christoffel symbol. This is simple. This is just rho lambda, and you just replace this with replace G with H. Of course, you're going to have higher order terms in H squared, but we don't care because we're at linearized level. So now you see that things become simplified. Okay, and therefore, similarly, your Riemann tensor becomes extreme. So if you linearize the Riemann tensor, then it just becomes again 1/2 eta sigma lambda. And you're gonna have partial mu, partial rho, h nu lambda. I mean, when you're writing things linearly, you can basically straightforwardly write down the entire thing, because of course we know that this must be two derivatives. So this is simple. You just write this term down. But then you know that this must be antisymmetric in mu nu. So then immediately you know that there should be a term that looks like this, where mu and nu is exchanged. But if you raise and if you lower the sigma here, then it's also going to be antisymmetric in sigma and rho. And this is related to the fact that these Riemann tensor, we can write it in a simple field strength language if we do things in terms of gauge symmetries, which we'll talk about in the extra lecture that we're going to have at the end of the semester. So that means we also have an anti-symmetrization between rho and lambda. So that means we're going to have minus partial lambda h nu rho, and then finally you both exchange mu nu and rho lambda, and you get a plus sign. So then you get then you get okay. So this is your linearized Riemann tensor. You see that it's extremely simple. And similarly, your linearized Ricci tensor is also simple. It's just 1/2. So you just, of course, you just contract this, and then you just have partial rho h nu. This is, of course, symmetrized, minus box h nu nu minus partial mu h. Okay, where from now on my h is going to be defined as h nu nu. Okay, so it's a trace of your. It's basically just. I mean, this is just equal to eta nu rho h rho nu. Okay. All right, so now you see that all of these, the Christoffel symbol and the Riemann tensor and the Ricci tensor is all simplified. And therefore, similarly, your Einstein equation. So finally, your Einstein equation is also going to be simplified. So the linear order Einstein equation, which we will be focused on at least this week. It's just going to be partial rho h. Of course, it's a two derivative. Okay, and this is equal to 0. Okay, so this is your Einstein equation. Okay, of course, if you have matter, then on the other side, you're going to have stress tensor here on the other side. Okay, now notice I'm doing linearized expansion in terms of my h here. So that okay, yeah, so I'm just going to leave it like that. Okay, so this is just my matter stress tensor. Okay. Any questions so far? This should be pretty straightforward. Okay, good. Now, remember that in the full theory, before the linearized theory, of course, we have we have our gauge symmetry. So I'm a little bit. I've asked some students yesterday. I'm not exactly sure how far you guys discussed this. I guess I asked this in the beginning. I don't think I really have a clear answer on this. So the gauge symmetry of general relativity is, of course, there's various ways to say this. Either it's diffeomorphism, Einstein symmetry, or some just say it's coordinate invariance. But at the end of the day, it's all just about you can transform x into some x plus some arbitrary function of x. And the system should be invariant. Okay, so it's really invariant under coordinate transformation. So at least this idea has been discussed in the class, right? Any response or no? Anybody?
Yes.
Okay. Okay, I hope it's been discussed and emphasized, because this is extremely crucial. So GR or gravity is invariant under what coordinate chart you use. Okay, and actually this means something something that is, let me just make this comment here, something that is very important about gravity, which is that in gravity there's no notion, there's no, sorry, this is a side comment, just give me 5 minutes to explain this, and you'll see this more and more concrete as you, if those of you who are interested in doing research in gravity, this issue will be more and more sharp. And that is that there's no local operators in gravity. There's strictly no local operators or observables. In gravity. Because this coordinate transformation is a symmetry, but notice that the symmetry is a local symmetry. This is what we call the local symmetry. Okay, or more precisely, or in other words, it's a gauge symmetry. Okay, if it's a gauge symmetry, then that means that it's not physical. So anything that depends, so anything, the only thing that is physical that we can discuss rigorously is gauge invariant objects or coordinate invariant statements. If it is coordinate, and if it's only coordinate invariant statements that we've seen this in various different ways. But if it's only coordinate invariant things that we can talk about, then there's no sense about local operators, right? Because if you talk about anything that is local, that means it's coordinate dependence, right? So you have some, if you have some operator O, let's say there's some observable O that depends on X, even if this is a scalar, operator, you know that this is when X goes to, when O, X goes to X prime minus, you do a coordinate transformation, this is not zero, right? Because it depends on X, right? So any local operator is not a gauge invariant operator. So in this very precise sense, because of this issue about gravity being a coordinate invariant theory, that tells you that there's no local observables in gravity, and you can understand this in a very precise physical way. And what is that? And so this is very different than all of the things that you guys have encountered before when you talk about quantum mechanics, when you talk about classical mechanics and electrodynamics. Every time there's a sense of local objects, local observable, either the precise location of something or the precise momentum of something, but there's always this local observable exists that is well defined. And gravity is not well defined. And this is very simple to understand physically. The physical understanding is the following: what is a local? If something is local, what that actually means physically is that you can define this, you can measure this thing arbitrarily sharp, right? So if something is has a precise meaning in space, you can you can go arbitrarily close to that point and measure it. Okay, I mean theoretically, of course, technology that's a different question, but there's nothing stopping you from measuring something at extremely sharp position locally. Okay, in usual theory. But what do you need to do to measure something that is local? You need to have some probe. And as you know, that as the area that you're as you increase the precision, what you do is you actually increase the energy, right? That's the usual notion. The higher the energy, the smaller the scale. Now that's what happens that's actually exactly what went wrong for gravity. And so if I want to measure anything arbitrarily small, I need arbitrarily large energy. In quantum field theory, there's nothing wrong with doing things with arbitrary. I mean, in the theory itself, there's nothing wrong. I mean, there's a lot of things that can go wrong, but a priori, there's no obstruction for us to measure anything at arbitrary high energy. But in gravity, there is a fundamental obstruction, because at gravity, so let's say if you have some region here and you want to, so if you want to measure things for this region, okay, so I want to do measurements on this region here, what do you need to do? So you basically, for example, and if we're just particle physics, so we'll start doing collisions. And we do collisions at arbitrary high energy. So the center of mass energy, you make it, you tend to infinity, so that the area that you're probing is smaller and smaller. But you know that if you talk about a theory of gravity, you're going to have a problem, because at sufficient high energy, what you're going to do is eventually the energy you're imparting in this area, as you go smaller and smaller, is eventually it's going to be smaller than your short shell radius. So at arbitrary high energy, what you're going to generate a black hole. Okay. So once you generate a black hole, of course, then there's nothing for you to measure, because you're not going to see anything in the event horizon. Okay. So it's so this is a very interesting thing, that there's a physical understanding and there's a mathematical understanding, and both understandings are extremely simple. But it's kind of interesting. Once again, the mathematical understanding, that since you're talking about you're talking about something that is coordinate independent, anything that transform under coordinate is not a well-defined observable, because it's coordinate dependent, right? So that's just a simple one-liner that tells you that there's no local operator. There's nothing local that you can actually say precisely in a theory of gravity. On the other hand, on the physics side's point of view, it's also extremely simple. What do you mean by measuring something that is local? That means that you want to go at higher energy to measure something very precise. But in GR, you know that at sufficient high energy, as long as when the area contains energy, the area of the energy is actually smaller than its short shell distance, you're going to form a black hole. So if you want to probe something small, you put higher and high energy, but eventually you must form a black hole. Once you form a black hole, you cannot measure anything beyond the event horizon. So there's a fundamental obstruction for you to define anything local in the theory of gravity. Okay, and so of course we're in gravitational fields, and we're always talking about where am I, where are you, and then we're measuring different things. So we're still doing things locally. So what that means is that what the local observables that we're defining in our theory is actually an approximate observable. It's not really a well-defined observable. If you want to really talk about well-defined observables, then you can only talk about what is called non-local operators. Okay, so at the end of once we establish these things in much more rigorous detail, we'll discuss what are the actual observables that we can talk about in gravity. Okay. But anyway, so this is just so I want to stress that because of this coordinate invariance or this gauge symmetry, in gravity, there's really no local observable. So this is a very important aspect. But okay, so coming back down to Earth, so we know that we have diffeomorphism. So I'm just going to call it diffeomorphism. So of course, the linearized theory also has diffeomorphism, and that is And that is my metric H mu nu under diffeomorphism transform as H mu nu plus partial mu cosine nu x. This is symmetrized, but I'm going to write it. I'm just going to write the symmetric part. Okay. So the diffeomorphism in the linearized theory just tells you that my metric transform in this way. Okay. So there's a redundancy. There's a gauge redundancy, and the gauge and the usual gauge fixing. So we fix the gauge, or the usual gauge that we. Is we use I'm called the gauge fixing condition. Is the usual one is, or not the usual, or the convenient one is written like this. Which is called the Dunder gauge. Okay. So actually, let me ask this question. So the fact that you have gauge symmetry and you need gauge fixing condition, I'm not exactly sure if you guys discussed this in the previous class. So is there someone that you don't understand this that you would like me to explain? If not, I'll just move on. So if you can just speak out, or you can just privately send me a message, or you just raise your hand. And so everybody understand what this is doing? Maybe raise your hand.
Sorry.
Yes.
It's the same with in the spin one field, like photon.
Exactly. This is the same with the spin one field. So good. Okay. Maybe I'll just do a 5-minute explanation. Exactly. So this is the same.
Thank you.
Yeah. So in the spin, as you know that so in Maxwell theory, your action is basically minus F mu nu, where your F mu nu, your Maxwell field strength is partial mu a nu minus partial nu a mu. And there you know that your spin one gauge, or you can do a transformation. You can shift this by a mu plus derivative mu on some arbitrary function that we call rho x. My F mu nu is not going to change, because it's going to change into partial a plus partial mu partial nu alpha x minus partial nu a mu minus partial mu partial nu alpha x. And so you see that these two cancel. So this is actually the F mu nu goes back to itself. So that means that your Maxwell action is invariant under this transformation, under gauge transformation. Okay. So that also means that anything, so if you have a configuration, so if you have, let's say, let me just write some random thing. So if you solve your Maxwell equation, you get a solution where F mu is some particular function, F mu x. I'm going to add this function, anything that looks like this. This corresponds to exactly the same solution, or sorry, if I have some solution that looks like this, then I add to this solution an arbitrary derivative acting on alpha x. That describes exactly the same physics. Okay, so it's exactly the same thing here, and we're going to have a homework problem about this. So it's basically the statement that if you do the linearized part of your action, if you do this transformation, the action doesn't change, which means that if you change your metric, so let's say if you have a metric solution, and then you add this kind of derivative terms to your solution, you're actually describing exactly the same physics. Okay, since you're describing exactly the same physics, that means that the degree of freedom, or the degree that is encoded in these gauge transformation, are fake degrees of freedom. They're not really real. Okay, since there's fake degree of freedom, sometimes we would like to remove them. And if you want to remove them, that's what the gauge fixing condition means. So this is this is actually, sorry, let me just erase this. So this is actually something. So basically, if you have a gauge symmetry, you want to break the gauge symmetry, and to break the gauge symmetry, you do the gauge fixing condition. So it's kind of fun. So this is like 元宵节灯谜. You can ask, what is the thing that you need to break in order to fix? Or yeah, and that's gauge symmetry. Okay, anyway, so but usually usually what the gauge fixing condition that we choose is the de-Dunder gauge. So what does that mean? So of course, generically, what we're going to have is, let's say if you have some h nu, then you do this derivative minus. Of course, there's no reason that this is 0, so this can be non-zero. So let me just call it f of nu x. So generic, this will be non-zero. But then, because we know that the physics is invariant under this transformation, so that means I can do this transformation on my h, right? So I can do this transformation. So let's do it. So now if I plug in this transformation in my h, then I'm going to get partial mu h nu minus box cx plus partial mu c mu x minus a half partial nu h. This is this h is the h contracted with, so h, remember, is just eta mu nu contracted with your h mu nu. So that means I have acting on my h plus 2 times partial mu c mu of x. Okay, so this is how this condition transforms. Okay, so we can just write things out. So of course we have, then this is just equal to partial mu h mu nu minus a half partial nu h. So let me just, this is the original part out. Then I have minus box c nu x. And so this is plus partial mu. So this is plus this guy, but this guy is the same as this guy, but this guy has a minus. So these two cancels out. So then you get this. Okay. So since before you know that before you already know that the thing that you started with is f of nu x. So this is just f of nu x. Sorry, this should be lower indices. I've been sloppy about the position of my indices. So now I can, as long as I have my c nu x to be equal to 1 over box f of nu x, then this can be 0. Okay, so starting with some non-zero configuration, you can just do a gauge transformation. And do a gauge transformation. If you choose your gauge transformation parameter in this form, then you can reach you can reach the de-Dunder gauge, which is that the partial mu acting on h mu nu minus 1/2 partial nu acting on h is 0. Okay, and when you reach this gauge, because you already fixed, so in order to reach this gauge, you already fixed your gauge transformation parameter. So now you no longer have your gauge degree of freedom. That degree of freedom is completely removed. Okay. Any questions? So of course, this form of de-Dunder gauge is really just a linear version. So of course, there's the there's the nonlinear version. For those of you who are interested, the nonlinear version of the de-Dunder gauge. The nonlinear version is g mu nu This is the nonlinear version. And you can show that indeed, if you linearize this, you get back the linear version of your Didonder gauge. Okay. Okay, good. So if we use the Didonder gauge, then we can simplify the Einstein equation. So let's see how the Einstein equation simplifies. So let's come back to the Einstein equation. So here's the Einstein equation. So let me just okay, so let's see how the Einstein equation simplifies in the Didonder gauge. So remember, in the Didonder gauge, I'm just going to write it in gauge again. So in the Didonder gauge, we have we basically have partial mu h mu nu minus a half partial nu h is equal to 0, right? So if it's or I'm just going to use this. It's going to equal to that. Okay. So now we can simplify this expression. Okay, so let's just write it out. So whenever we see this contraction, we're going to replace this with 1/2 derivative on this guy. So for example, for here, since you have a partial rho acting on h nu rho, so that satisfies this condition. So in the Didonder gauge, I can translate this into 1/2 partial nu acting on h. Okay, so this is going to give me partial 1/2 partial. This is going to be partial mu, partial nu, acting on h. Okay, but of course this is symmetrized. So these are symmetrized. So if these are symmetrized, there's partial mu, partial nu, and there's also partial nu, partial mu. So that just means that there's an overall factor of 2, and I can erase this, and then I'm going to erase this symmetry factor. Okay, good. So and then sorry. And then the next term here, there's nothing changed. Nothing happens for this term. So this is just box h mu nu. And I'm going to have a minus h mu h nu h from this guy. And then I'm going to have a minus 8 mu nu. Here I'm going to have partial rho, partial sigma acting on h rho sigma. So once again, the Didonder gauge, it looks like this. So if in the Didonder gauge, I act with another derivative, partial nu, partial h mu nu, this is going to be 1/2 box h. Okay, so that means that this guy here is just 1/2 box h minus box h. Okay, and this is going to be equal to T mu mu. Okay, so now you see everything becomes extremely simplified, right? Because first of all, this term cancels out, and these are all just the same. And then you're going to have, so basically what you have is you're going to have this term and this term. So you just have, so this is minus a half. This entire thing is going to be minus a half. So then you're going to have box h mu nu plus a half eta mu nu. Box h is equal to T mu nu. Okay, so this is the simplified version of your Einstein equation at the linearized order. So if you have some source and you just want to consider linearized in your fluctuation field, then this is the equation that you have. And actually, we can even write this in even more simpler. So if we define h bar mu nu is equal to h mu nu minus a half eta mu nu, which is obvious that you want to do that here, right? Because this is just an overall box. Then if you redefine this object here, and of course you can, once you derive h bar, you can derive h. Okay. So that tells you that the Einstein equation at the linearized order is simply just box h bar mu nu is equal to minus, so let me put back the 16 pi g t nu nu. Okay, so this is the linearized Einstein equation. And for those of you who are familiar with electrodynamics, you see that this is very similar to the linearized equation that you have, which is, sorry, usually we write it as a current. So this is like an echo of the Maxwell equation. Okay. Okay, so this is a linearized Einstein equation, and so from now on we're going to try to solve this equation. Okay, we're going to try to solve the linearized in the linearized limit. Is there any questions? Okay, so but before we do that, so let me just mention some other things that one can do. So this is this is the linearized equation that one can get from expanding out around flat space. Now, of course, we can go back to here, and we can go back to here, and then consider another background here. So, for example, we can consider short shell background. So we can plug in the short shell metric here. So let me just do. So let me just do and we can put in here short shell metric here, and then plus kappa h mu nu, and then this will be describing a fluctuation around short shell background. Okay, and as I mentioned, this will be we can do this the fluctuation around short shell background. We can take any black holes, and we can take Rice and Nordstrom. You can take Kerr black holes, and then you plug in the background here, and then you write down this fluctuation. And then you plug this into your Einstein-Hilbert action, and then you do exactly the same thing. You perturb around this to get to the linear order equation. Okay, so this is going to be your homework today. So this is, I'm just going to write down the homework for this week. There's going to be 2 homeworks, but this will be a homework, and I'm going to announce the project, the first project. So today the homework will be the following. Well, so you can first do a warm up, okay? So you can first do a warm up. So you can first. So this, okay. Let me put it in two steps, 1 and 2. Okay. So 1 is derive. So you can follow my steps again. So first derive. So I already derived it for you, but just for you, derive the Einstein equation to linear order in h mu nu around flat background. Okay, so this is already done. Second, derive the Einstein-Hilbert action. The Einstein-Hilbert action to quadratic order. So that means to h squared. Okay, the linear order will vanish. So you need to show why. Okay, the linear order, and you just get the quadratic part of the action. So these are straightforward. Yeah, try to do this in the Dedunder gauge. Okay. Now the third problem is again derive the Einstein equation but this time again to linear order, but this time around short shell background. So I've decided to decided to break apart the projects into first a few series of homework. So this is part of what you need to know for the project. So you need to derive the Einstein equation, at least up to linear order and short shell background. Okay, so these are the three things I want you to try your hands at today. Okay, so we're going to have two projects. So one is about the perturbations around black hole backgrounds. Okay, so these are the homework. Is there any question? So this will be due next Monday. Okay, great. So since good, so a little bit preview about what we're going to talk about tomorrow. So since we see that the equations here, are very similar to the equations here, that means that the solution should have some similarity between the solutions that you have for your Maxwell equation. Now, since you have similar, for example, for the simplest solution that you can think of in terms of Maxwell equations is, of course, the plane wave solution. So we're going to talk about what kind of wave solutions do we have for the linearized gravity. But before doing that, let's just count the degrees of freedom that we have. So how many degrees of freedom do we have for h mu nu? Okay, so of course we're going to have box. So of course we're going to have box in flat space. We're going to have box h bar mu nu x. Sorry, not in flat space, but without source. The Einstein equations tell you box h bar mu nu is going to be equal to 0, right? So that tells you that if you expand h bar mu nu x in terms of plane waves, so let's say if we do it in sorry, what am I doing? Okay, so let's say we do a Fourier transform using the plane wave basis. The fact that this is 0, the fact that box acting on this is 0 is telling you that k square has, this tells you that k square has to be 0, right? So that means that this H field in terms of momentum space are massless like fields. Degree of freedom. Okay, so just from the linearized Einstein equation alone, you already know that these the fluctuation degrees of freedom are essentially massless. Okay, so that means that dynamically these fluctuation will travel at the speed of light. Okay, because these are just massless fields. Okay. Any questions? So furthermore, since h mu nu x or equivalent going back to the original h mu nu, since h mu nu x is unchanged by a transformation, okay, that means that actually you can use these transformation to remove 1 degree of freedom, a vector degree of freedom from your h mu nu, right? So let's say if we do the gauge fixing, let's say we fix h0 nu to be 0. Let's choose this gauge because we have 4 degrees, so we have d degrees of freedom here. So let's say we choose to remove these component to be 0. Okay, then this means that you only have so you only have, so you can show that this means that you only have new, which is now running. So since H0 new is 0, so that means that you only have Hij, where Ij is only the spatial part. Okay. So you only have spatial part. So if you have spatial part, since this is symmetric, so you're going to have d minus 1 times, so this is symmetric, d minus d times d minus 1 over 2 degrees of freedom. Okay, but however, you know that they're light-like, right? You know that they're light-like, and therefore you know that since they're really light-like, so that means that really the degree of freedom that you have is really only the transverse part. So that means that you really have d minus 2 times d minus 1 over 2. You really only have these number of degrees of freedom. Okay. Furthermore, you know originally that if you guys remember, you know originally that this part, that the original metric is supposed to be, you're supposed to impose traceless condition. So you need to minus 1 degree of freedom. Okay, so this is the total degree of freedom you have with h mu nu here. Okay, so if we plug in d equals 4, this gives you 2 degrees of freedom here. Okay, so these 2 degrees of freedom are exactly the 2 degrees of freedom that is similar to the Maxwell field, where as drawn in class, that if you have a electromagnetic wave, you basically have 2 directions of oscillations that are perpendicular to the direction that you're traveling. And here, similarly, you have exactly the same thing for gravity as well. Okay, you only have 2 degrees of freedom in 4D. Okay, so tomorrow we're going to focus on these 2 degrees of freedom. We're going to derive it and inside them. We're going to show exactly, if you choose a particular gauge, where these 2 degrees of freedom sit in your metric. And then we're going to, we're going to analyze how they propagate, and depending on what kind of source you give them. Okay, so this will be our focus. So basically solving the linearized Einstein equation will be our focus tomorrow. Okay, so I guess we'll probably stop here. Is there any questions?
Yes.
Yeah.
Why does h mu nu have to be traceless?
Yeah, we're going to derive that when we're considering the propagation. Okay. We can derive it from the equation of motion. Anything else?
老师，我想要问刚刚一开始同学问的问题，就是关于上一次的那个作业。
哎，
可以吗？哦，好。
我们明天OK， 你可以先问我，明天再讲好不好？因为那个还有人，因为我是要到今天之前结束才交，才结。
不是，应该，因为，就是因为它那个，如果它那个方向的话，那要怎么去定义它？因为像刚刚那个一开始同学讲说，当他那个另外一边它的 t 的那个方向跟另外一边不一样，那这样的话，我们就不能用一开始那 t 趋近无限 r 趋近无限的方式来那个定义那个 square plus 啊。 哎，是吗？对，不一定去。对，好，
你现在讲是说，sorry，好吧，我先回来。你们现在讲是说，另外一边为什么上面是 scribe plus，是不是？
对，因为如果考虑到它的那个 t 的那个增加方向的话，就跟那个另外一边是定义的感觉不太一样。
sorry，我可能要看一下你们 explicit 的你们的 coordinate transformation， 但是 I mean 基本上你的 picture 是你的 light 你的 light 都是往上的45度，在你的这个 Penrose diagram 它一直都是往上的45度啊。所以你说为什么 scribe plus 都在这个两边？我不是很清楚说这个是有什么问题，它都是往上的45度是你的 future infinity。
我觉得我要写的好了。
OK，
OK， 好，好。那我要发电子邮件问，还是在课上问
OK， 没关系，你可以发电子邮件，反正我明天等到截止，我明天可以统一。我看大家好像对这个问题比较那个，这次作业比较有问题，我明天会对这次作业做回答。好，我明天一开始先针对这个作业，这次作业那个就是我们就 derive 一次给大家看好。
好，
你可以先寄信给我。
好 ，OK， 我寄信好。
OK，
好，
好，那我们今天就先这样子喽。好，谢谢。
好，谢老师。